Okay. Hello everyone. How are you guys doing today? New week. We have just crossed, 5 days of things. I hope you are done. You're all good and you made use of your time on this last weekend to brush up of some of the things that we discussed. We're almost there, right? We are almost there in terms of good, good. Thanks a lot. Thank you. Thanks for asking. Let's start with a little recap of what we did here last week, right? I'm not sharing any screen right now. I will share. Okay, let does this be a two-way conversation via the chat, I would suppose. And is there any questions that you have? Is there any questions that you have got, some sort of epiphany that you have got over the weekend, or something that you want me to, reiterate? This week is going to look little easy in the sense that now that you've understood, or you're in a path to understand how what is this neural network, and how what is a deep neural network, and what is deep learning means, and what are its core foundations of it, right? Okay, right. Awesome. So so Uttam, right? So go through them. If you have any questions, please ping here or in the community link as well. And I'll try to respond to them. And I would encourage you to raise in the class in that way. Others can also know what sort of question that you have. Generally, learning happens outside the class, right? Do you have any questions? Any of you? Any specific topic that we have discussed that we want to reiterate? General equations. Can you explain again how the general equations leads to feature learning? Okay, right. Um, um, right. So what I assume that you mean that, okay, how do we learn features? Okay, we can do that. It's not a problem. We can go over it one more time as a refresher. Um, what else? Do you have anything else? So I in fact just before, I think couple of hours back or 1 hour back, I have shared, I have updated a in like 15 or so, I think some 10 minutes, sorry, half an hour back, I have updated in the community link. Does everybody have access to the community link? Can you go down? Can you go there and download all the things that we will be taking today? I think there are two zip files and two images that I have put. I would want all of you to download that and keep it in your lab. The images, can you share the link? Okay. Okay. So I was there, so I can just share the link here. I hope this helps. So this is the way we are. I've been asked to actually share the content from there. That way, all of us can access it. Please download all the contents from here. And how logistic regression is, right. Actually, yeah, we can do that. Then how it is different? Same. We are not doing same thing. We are not at all doing same thing in neural network at all. Okay. So I think the nice. Anyone wants to answer that? Anyone wants to write in couple of lines what is the difference between a logistic regression and a neural network at a fundamental level? Anyone wants to answer that? What is the fundamental difference? What is the fundamental difference between a neural logistic regression type of of a problem statement, of a solution, and neural network? You remember these terms called as parametric and non-parametric? One had an equation, neural networks tries to define the equation as it goes, right? Um, it's not no, so neural networks are also good at classifying structural data. It's and in fact one of the things that we'll see is today. The fundamental reason is that neural networks are non-parametric. We don't know the equation form. Remember, we derive the equation, right, as and we go, right? And in logistic regression, one of the things that we do is feature engineering, right? Human beings generally have to do the feature engineering. Here, neural networks do the feature engineering. to some extent, to a lot extent, right? So there was a question, I mean, I am used to optimization problems, but I cannot see how can the program's intelligence can learn from the data set. So we have gone through this, right? Is that, how does, let me share my screen. Okay, let me just share my screen. Okay, let me open some, just give me a minute. Let me open some, this, or, okay, this one is here. So we have, what do we have? Where do we should go? Okay, just give me a minute, guys. I'm just opening my art drawing. Remember our drawing? We'll just open the drawing and maybe we can discuss against that. Maybe it's easier that way. Okay. Right. Okay. No, I think there's just, it's not the one difference. There's a bunch of differences, a lot of differences. The logistic regression is what? It's fundamentally a linear model, right? You give it a non-linear data, will it work? If you give logistic regression a non-linear data, will it ever work? Do you think it will work? No, right? So, and all around us we have, hundreds of, everything is mostly, non-linear data. Okay, so this is right. So this is one of the big difference. Everything is non-linear data, right? Remember that? So how will it work? It will not work, right? And also the scale of data, will it be able to handle it? It will not be. Okay. So is it the iterations or the parameter weights that, okay, so let's talk about this. Let's talk about this. There's a good set of questions that are coming out. So the question that is coming out is, how the general equation leads to feature learning. How is it even learning? What is this idea of learning? I cannot say the program intelligence can learn from a data set. Okay, is it iterations on the parameters weight or successive optimization steps? That leads to, I think it's a combination of all of it, right? So do we remember our model? Our problem statement was given some feature. We had 4 samples, right? Remember, we had 4 samples, and we said that each of those 4 samples had one feature, right? So it's going to be one vector, right? So basically one feature. So it's going to be one matrix, which for this example that we took, right? And what we did is that we went through all these, circles which did 2 operations. Remember, aggregation and activation. Activation is nothing but non-linearity part of it, and they were trying to do something. And it turns out that what they're trying to do is that they're, in the terms of neural network, we were actually building hidden layers. So what was it trying to do? It was trying to actually, so output of each of the hidden layer is something like this, which means that this is nothing but a transformation, right? Now, this kind of transformation is very common, right? You can also do this kind of transformation if you have a function. That is what we used to do it. If you remember, in the traditional machine learning world, we have polynomial transformations, right? A lot of transformations are there, right? So you can apply that, but in this case, the machine is trying to do it, right? The algorithm is trying to do it, and we are trying to learn hidden latent features via that non-linearity part of it, isn't it? You can add many such things, and various types of hidden attributes are coming out, which was very difficult for human beings to figure it out. One of the things is that these outputs of H1 and H2 and H3 layers are, so the output of H1 layer was actually a direct transformation from input. However, if you remember, the output of H2 is a direct transformation from the previous layer's output. Did you ever do something like this, that you've taken one transformation and then again transformed it back to another transformation? Very rare, right? You did PCA, suppose you have 100 features, you did PCA, and then you've got something, and then did you ever do PCA? Will you ever do PCA? I mean, nobody's stopping you. You can always do, but will you generally be doing? Very rarely, right? So in this case, the intuitiveness is, technically you can do whatever, right? It's just code. You can write and do whatever it is, right? So, but intuitively, what we are trying to say is that each layer is trying to extract a part of the data, or trying to extract and transform the data in some way so that it represents something. And this representation, maybe from the image, it is trying to find the edges, right? Maybe from the image, it is trying to find the nose or the eyes. One layer will look at the eyes, another layer will look at the face, another layer will look at only the edges, maybe the hair, and so on and so forth. And combination of these layers independently, when they combine at the last layer, will say that, okay, I can now build a face, right? So one of the critical things from a learning standpoint is that these output layers these outputs are nothing but hidden feature representations, right? Which are so hidden that it is very difficult for humans to do it. That is one way to, you can say that I can actually build a layer in such a way that it will only detect face, right? So that's sort of an intelligence. I don't know whether you can call it intelligence or not, but that is definitely way to represent a feature, isn't it? So that is one thing is for sure, is that we can see some sort of feature representation coming out of it, right? And we know that for any machine learning algorithm, features has to be great, good, and we'll come to that. This is why W metric should contain different coefficients. So yeah, absolutely. You're right. Right. So the numbers, so all of this is a number, right? So this is a number, your input was a number, everything is a number, right? So one thing is that one ideation of that, is this intelligence or is this learning? The network in this case is trying to learn these outputs, and these outputs, right? It is trying to learn, right? It's trying to not only learn, it's trying to optimize, right? By how we'll come to that, but essentially this each one is trying to only detect the nose. This H2 is all about that edge, or this H3 is all about the hair. And more epochs we do, I think the nose detection layer will be good. The hair detection layer will become really good, and the edge detection layer will actually become good. If you combine all of them, overall you can actually detect a face, right? So one is this, feature representation itself, right? The hidden feature representation, which itself is you can say that this is definitely something it is learned, right? Is it the iteration which learns? Absolutely, right? So, overall, we've seen that, right? So to accomplish this layer, we have this many number of weights, right? We have total 40 weights. We've gone through this, remember? We have got 40 weights and biases. We have total accumulated weights and biases are nothing but 40 total, right? Now we have also found out that at the end of it, loss is loss is what? Where did we write that equation? I will come back to all of this, but we said that loss only depends on weights and biases, right? Loss is something that we can only depend on weights and biases, right? So how each of those things are connected is how we can do it, right? So if you change the weights and biases, and that's how your H1 will become. If you want to be really good at the edge detection or the face detection or the hair detection, which are nothing but features, I have to find that optimum weight, that classic optimum weight, and that is where the learning basically comes out, right? How are we fundamentally learning? And so we have to continue to change the W's and weights because we start from random, and iteration is definitely one of the ways to do it. We iterate as many number of times. But why are we iterating? Do we know why are we iterating? Yes, exactly. As for example, because we are trying to optimize this problem of minimize the error, right? Now the thing is that if you used to solve optimization problem, right? You said you used to solve optimization problem, and what does an optimization problem says, if you look at any of the optimizers that we have looked at last time, its only objective is to reach to the global minimum, right? 100%. If you run it n number of times, given a chance, suppose remove the machine learning equation out of it, okay, you can run any of the optimization problem. Your objective is to reach to the global minimum. But we know by hook or crook, it will always reach to the global minimum. Now we know one thing, if you add the machine learning part of it, right, is your objective to reach to global minimum? Can anyone answer that? Think about it, right? Is your objective to only reach global minimum? What happens if you do reach global minimum? On a training data set, if you do reach global minimum, what do we call that? On a training data set, if you do reach global minima, what do we call that? Yes, now, yes, exactly. So you are trying to overfit it, right? But from we are machine learning engineers, you have been telling me for last whole week and for a whole year that overfitting is bad. Overfitting is bad. You cannot learn too much. Machine learning says overfitting is bad. So you can be very close to global minimum, but don't go to global minimum because then there is a very high chance of learning, memorizing things, isn't it? Now, but optimization is what? Optimization is all about somehow reach that global minimum. So in a way, if you are someone who's coming from optimization, it's actually the other way around of machine learning, right? It's actually two different side of it, and somehow both come to picture. Are you able to appreciate what I'm trying to say, right? It's like optimization is trying to solve the global minima problem. Machine learning problem is saying that please do not just reach global minima. I appreciate that you want to reach, but just don't reach there. Stop somewhere else so that I don't so that you don't memorize things. Okay, and so that is one thing that one has to realize, okay, because people who actually are building Adam or SGD or any of such flavors, they don't care about machine learning problems, right? And machine learning says that, okay, I will use you, but only till that moment where you don't get overfit. That is the reason we have created a different algorithm called as regularization parameter, isn't it? Which is outside optimization in neural network or even other thing also. It is outside optimization, isn't it? That we should not learn overfit. Coming back to the question that how are we learning? How can you say that we are learning? So I think I said that one is this feature representation extremely important. You will see now, I mean, we will not touch a lot on CNN because this is not the scope of the course, but in typical language models or even for the image, right? You will see these features are so good, like they are like so good, they become so good you can use them as it is outside also. So I can actually build the model and cut it here, okay, and say that I have an awesome feature representation, and you can use this model with, you don't have to train anything, just change your last layer, okay, just add your own custom layer and start from there, because my model gives you a very good foundation of learning objects. This kind of concept is called as transfer learning. So you already have a knowledge base. Start from there. Don't start from everything. So this is definitely, feature representation, feature understanding is definitely learning, no doubt about it. And there's a lot of effort has been spent on tuning these ways of doing, this feature representation, finding the best feature representation given a specific data. Okay. And how are we doing it? Okay, we said that how are we doing it? We said that we build this function, big function, right? This is nothing but a function of a function of a function, right? And there was a question, right? If this has been a linear regression, what is the linear regression equation? I have put it here actually. This is logistic regression. Okay, good. The question matches. So we've discussed this actually, right? So if this is in retrospect of logistic regression, what are we talking about? Remember how many features we have? We have x1, x2, x3, x4. What will be the equation of logistic regression? I mean, at its core, the line equation. I'm not talking about the final probability distribution. I'm talking about the decision boundary, right? So, do you guys agree to the fact that the lines equation, or in this case, the hyperplane equation, will be like this: m1 of x1, m2 of x2, m3 of x3, and m4 of x4, right? That's also not true because we have only one feature, right? This is wrong. We said we have one feature, so this is not true. So it's basically mx plus c, right? So how many features in our original data set has? We have only one feature, so it will be only mx plus c, nothing else. So what did we learn? In logistic regression, how many coefficients that we are trying to learn, or weights and biases, for this particular problem statement? 2, m and c, 2, right? We are trying to learn 2, m and c, slope and coefficient, right? And in this case, in neural network, we see that there's already 40 weights, right? So there's clearly like just 2 versus 40 has no comparison. It's 20 times more, right? And we can add more things on the same sort of data set, right? So which means that you're trying to learn 40 things, but in case of logistic regression, you are hardwired, and there is no way you can actually go beyond it to learn more than 2, right? That is a fundamental difference, right? 2 versus 40, no brainer. And for people, someone who learns 40 things from the same data is already a master, right? There's a question that been said that in optimization, inputs data set is unique and static, right? And the solution apply only on that data set. In machine learning, we are trying to look for non-perfect, one-fits-all solution to reach to the same objective on different data sets. That is absolutely correct. That is the reason we do cross validation. That right? That is the reason we do cross validation. That is the reason we send that validation set and we say that stratify yes every time we send that validation set. Sorry, train set, change something. Even if you add the dropout layer, what happens? This will continue to change. So basically, the network is seeing different type of data, isn't it? That is correct. So we are trying to build the general intelligence at some point in future, which will be one problem or one probably non-perfect, but it should be a way that you can learn as you go, right? You can start from somewhere, you have a good base, but as and when my new data comes, if I train again, I should be able to, gather some more intelligence out of it. This statement is absolutely right and absolutely fun, absolutely right. So, we take these two different fields. You take a research scientist from optimization field and a guy from machine learning, they will actually fight because they have two different agenda in that room. Okay, literally, they will have different agenda and they are basically a colliding agenda. And now, as an ML engineer, you have to keep both of them at calm. Say that, okay, guys, don't worry. I am here. I will listen to both of you, and somewhere we will meet so that we generalize all these things very well, right? Since we are discussing this, let's continue on this, right? Any questions on this? This is very important. Let's discuss one of these things. So now we have said that now from the ease of it. So this is our cost function. What is the cost function? It's like the big thing, right? Optimization will do what? What will an optimization do? You give an optimization guy a cost function, he will try to minimize this cost function. His only objective is to minimize this cost function and nothing else. In fact, if you give that guy a function, his objective is to minimize or maximize. Go to the extremum of it, right? Any one of it, and whatever you want the objective to be. So this is the cost function, and all these algorithms are trying to reduce it. My objective is to reduce this function. This function was built what? Nobody knew the function. The network built the function, right? And this function can be more deep. So in non-parametric sense, I can see that L of F of G of H of I of W's and B's, nothing but W's. This is a functional form of way the non-parametric neural network estimator or a model will generally work, which can be represented as a computational graph. Okay, it is actually represented as a computational graph in frameworks like TensorFlow, PyTorch, because of reasons which are really important and for the compute need. Okay, it's easy to build it, right? So that is the reason in machine learning everything is a function. Your data is a function. Everything is represented as a function because you can represent in a computational graph, and because of what? What is the other thing? Functions are by definition. Functions are by definition. Something else is there, right? You need to go back and update something, right? What do you do when you go back? What happens when you go back? What happens as a part of my backward propagation? Do we remember? What is the fundamental thing that happens? Anyone? We need to find derivatives, right? So function are first order differentiables, right? They can be differentiated. We can find the change. We can find, you can get those gradients, and you can compute a differentiation. Why do we need to compute a differentiation? Because we said this sentence that losses to compute this cost function, everything is nothing but weights, right? And my only objective is to apply new weights, right? Yes, you adopt the weights, right? So this is a generic equation of adopt the weights, right? When you did the forward pass, you've got a new set of weights, isn't it? And when you did the backward pass, from the loss, you found out that I need to update each of my weight has to be changed by in some manner, right? Some will become minus, some will become plus, whatever it is, right? And this is the general equation, right? If I have my new weight is nothing but my old weight minus some learning rate. Remember the learning rate? Learning rate is nothing but a hyperparameter, and then this differential equation, and then this partial derivative of loss with respect to my old weight. If I can compute this, then I can put this equation, and then I can get my new weights, which can then be applied by my optimizer. So if I have a new weight, so this is my weight, right? So because this is my cost function, this is my cost C1 because of a bunch of W's, right? Because of bunch of W's, right? So suppose this is W1. This cost function is because of my W1. Clear? Now I am not satisfied. I have to go down here. So to here, go down to here, I said that I need to change my W1. How will I change my W1? I will do a differentiation between my cost and weight and apply this formula to arrive at a W new one. Once I apply the W new one, I will traverse the W new one, and so this is my W new one. So this is my C2, right? Sorry, this is my C2. This is my cost, second cost, right? Learning rate is nothing but it's a hyperparameter. It's like a, yeah, it's basically it's a hyperparameter. You can consider this as a step size, but you know it's the step size is something you can consider this, but basically we get step size from learning rate. But for now, learning rate is a hyperparameter. So how do we get C2? We have got the C2 based on this new weight, right? Underscore new, isn't it? So because of this new weight, I have got, sorry, because of this W old, right? I have got my C1. Now I have got my W new, which will get me my C2, and that is what I do. I continue to do this till I reach, my objective is to reach here, but not exactly, right? I cannot reach here because I will learn a lot of things. I will memorize it. I will overfit myself, right? So that is exactly what I do, and this is the general equation of applying the weight, and it turns out that this particular partial derivative is not that easy to compute because I have to look for all the partial derivatives that it impacts, right? So if you apply the chain rule, we have gone through all those things. In our case, if we apply the chain rule, so how many functions we have? We had a loss. So if you so this is exactly what we have loss function L, F, G, H, I, and then these are my W's and B's, right? And I have to reduce this. So if you apply my chain rule, this will be my chain rule, right? For every such weight, right? For each and every, all of those 40 weights, I have to compute my dl by dw. In other way, right, what happens is that I can generalize this function in a matrix form, right? If you have a matrix of all old weights minus the learning rate, and I have a matrix of all the dl by dw's, I can actually compute a whole new matrix of w new, right? This is something that I have given to you guys. So essentially, this is what we call as a negative cost gradient, negative gradient of the cost, right? We can compute this. This is nothing but this array. This is nothing but a matrix, right? And this matrix can be expanded into this form, right? For each and every weight that we have, I have to compute this, right? And that is what backward propagation, the power of backward propagation is to make this computation extremely efficient. And I will make an explainer as well, and we'll definitely have time to go through this. So how can we solve this is a question that will come up for later this week. Don't worry. Okay, but finally I will compute this big matrix, apply this, I'll just simply do a matrix multiplication with my learning rate minus with my W old, I will get a new W. Again, it depends on, this equation might change here and there based on what optimizer we use, right? Remember, someone will add momentum, some will add Nestrov's, someone will add, if you go to Adam will add what? Do we remember? What does Adam add? What does Adam add? Adam will add both momentum and properties of RMS prop, right? It will add both. What was RMS prop giving us? Do we remember? What did RMS prop, why was RMS prop good? Or that class of algorithms was good, better than the normal SGDs? I have also said, because, okay, what do you mean by eruptive? What do you mean by eruptive? Yes, they are adaptive. That's correct. So what is adaptive? What are they adapting to? Perfect. So in this case, absolutely correct. So this is the learning rate that you have to hard code. In RM Adams case, this learning rate is not a constant thing. You just give it a starter, it will continue to update down. Plus, it will also have that good thing about that SGD momentum thing. Remember? So it will combine those. That's a really good thing. So, but overall, this is what it is. That's what it is, right? And if you compute this negative gradient across like millions and millions of weights, you will have a really matrix like this. Backward propagation can compute this matrix in a jiffy, right? In such a way that it is extremely computationally efficient and give it back to you. You can simply do this matrix multiplication or minus this equation and get the new rate, and you will apply that. Your optimizer will apply it and reach to C2. That is fundamental, right? Okay, I think cool, right? This is good. I have given this, by the way. Okay, if you actually go to the community link and sign up, you should see that I have given this one as well. I have given the if you remember, we have gone through the explainer on the optimizers also. So that's an old explainer. I might be typos. Okay, I have not looked into and I have not cleaned it, but I think it gives you enough to understand that each has its advantages and disadvantages, and how do we actually reach Adam. Start from that normal gradient descent across various algorithms. We have reached to Adam. Adam is generally considered as great. By the way, just because Adam is great, that doesn't mean that others are not great. Okay, just the saying that Adam might reach at a volume, it might reach much faster. That's all it is. Okay, great. So what are we going to do now? Let's discuss two things. For our objective of today is like we will quickly see what is this vanishing gradient, and we have two more topics to understand. What we'll do is like we will actually open a Jupyter lab, a Jupyter notebook, and go through that. Okay, hyperparameter tuning and XAI. We will go through that and we'll come back and see whether from theory standpoint if we are missing anything or not. But what we'll do, so the hyperparameter, sorry, not X, hyperparameter tuning and XAI, we will actually go through a lab. I would strongly suggest you guys to please go and download all the material from here. Okay, oh, okay, there are multiple zips. Either way, you can download this zip file, all the zip files, the explainers are also here, and please upload to your, where do we upload? We upload to our practice labs. Please do that while we discuss vanishing gradient and exploding gradient, right? Yeah. This is also a good hands-on. So what we'll do is like we'll not spend much time on this. We'll probably spend 20 minutes and then quickly go through that. I want to spend most of our time on that, right? Okay. It should be up, right? Okay. So I've sent it. Now please save it, all of you. Okay. Request all of you to please save the link, and you can ask questions there as well. So all this is good, but is neural network adverse or problems? Absolutely not. There's a big problem that neural network suffers with. Actually, there are multiple problems, but we will be discussing on couple of two problems which which hinders this learning, the idea of learning. One thing was very clear that how do we learn if we cannot compute this metrics, right? If we cannot compute this metrics, we are at loss, right? If all of them become zero, right? If this whole matrix becomes zero, which means my gradient becomes zero, which means what will happen here? This term will become zero, which means my W new will become W old. Clear? If this term becomes zero, my W new will become W old. And if my W new becomes W old, then there is no learning. At that point, my learning stops. You are not learning anything. So you are stuck in this ladder. Where are you stuck? You are perennially stuck here, right? You are not going down at all, right? So that's the end of that network, right? So that is one way of understanding how important that gradient computation is. And since all of these are numbers, right? All of these are numbers, right? it's an important aspect because numbers can become zero. You don't have any control of numbers. These are all very opaque numbers, right? It's a black box. You actually do not understand. I mean, we will discuss it, but you actually are not very sure about what of these numbers represents, right? All this, isn't it? But they can become zero. They can become so less that a differentiation of that number will become always less, right? Right, isn't it? So that is a problem that exists, saying that if your gradients goes to zero, we call it as a vanishing gradient. Gradients is vanishing, and this just generally started coming on when deeper and deeper networks started occurring, right? When the 5 layers network was fine, you bump it to 10, 20, 30, start 40, and you started seeing, okay, right? And so after 10 layers, nothing is getting learned. After 8 layers, last 2 layers are literally getting same inputs because there is no learning, it has stagnated, right? And so it's basically having better to not have any other layer. So this is the problem of vanishing gradient, and typically what happens is that it has a lot to do with when gradient becomes very small, subtracting it to the weight will basically cause vanishing gradient, right? So this is clear, guys. So this equation of my W new will become equals to my W old when my dl by dw old will become 0. So I have to ensure that we should not be 0, right? And how do we ensure that? So let us see what are the reasons. One of the reasons that is that it can be 0. Anyone? Let's see that what is the one reason that it can be 0. It is here, written here. Suppose we have chosen a function called as sigmoid in your hidden layer. Okay. Now it's not very complicated to understand. Okay. Sigmoid is what? Sigmoid has a limit, right? What was the limit that sigmoid came up with? Sigmoid, any number you pass to sigmoid, it will give you what? It will give you a number between 0 and 1, right? It's a very constricted number, isn't it? It's almost 0 and 1, though has infinite numbers, but it is a very small number, right? In terms of only returns 2 values, right? Now it gives you a range, right? It gives you 0 to 1, right? So as a result, what happens? As a result, what happens? Right? There is always a chance that the sigmoid operation might give you like 0.000029. It's a very small number, extremely small number, right? Because your range is very small. Same thing is with tan h. What was tan h's range? You will now realize why ReLU is so important, and one of the most easiest of function is ReLU, right? ReLU is nothing but max. ReLU is tan h is become -1 and 1. How many numbers that you can even have, right, between -1 and 1? This operation, so if you have your hidden layers with tan h or sigmoid, you are guaranteed to see this vanishing gradient problem if you have anything above 6-7 layers. Okay, and so if there is no big data anyway, if you have not much of a variation, right? Because the numbers will be doesn't have too much to change, right? So vanishing gradient is nothing but it becomes too small. You do a DL of you do that loss. Either the loss is extremely minute, small, has no meaning. It will take eons for you to go to the next step or to even converge, or it will become 0, right? So that is nothing but vanishing gradient. How do you solve a vanishing gradient problem? Generally, how do you solve it? Change your activation function. Look at your activation functions in your hidden layer. And all of these are because of in your hidden layer, guys, right? Your first and last layer has no problem whatsoever, isn't it? Most of these problems is in your hidden layers. And that is where you're putting all your effort to learn that hidden representations, latent representations, and try to learn them, right? And appropriately in such a way that weights represents to those, right? And if that becomes 0, your learning stops. It's almost as if you don't have anything. It will fall down to a linear kind of an approach, right? Is that clear? Does that make sense? Now, how do we prevent it? You can now you can appreciate this. Let's see how ReLU works. Do we remember what is ReLU's? So ReLU had this, right? And what is ReLU's this thing? So it started from here, and it is max of 0 to this 0 to, so if you have a number, if you have a number 0 comma 39, if you give it to ReLU, what will be the output of this? What will be the output if you pass this number to ReLU? Do you remember? ReLU is very simple, right? What is 39? Perfect. So max of whatever it is, right? So it's basically unbounded on this side, right? You can actually go here and at least n number of places, right? So it can actually go here, long to low, right? So at least that way, and ReLU is very simple. Like, and sigmoid as a activation function, if you look at it, remember 1 divided by 1 plus e to the power of minus that whole x, right? So that is also which part of the gradient, as in gradient comes in layers. Which part means which, for which layer the gradient is becoming 0? Is that the question that you are asking? No, so you will, how will you know that the gradient is, how will you know that you are not learning? When you are trying your epochs, maybe you are trying to run 100 epochs, after 10th epoch, what will you see? What will you see? Your validation accuracy or your training accuracy is not going down, right? It's basically no change whatsoever. That is the only way you will know, right? Okay, this system is not learning. And most of the time, it is because there is no gradient change. Not most of the time, all the time, right? Right? So that is what it is. If, for every epoch we print that, right? So you will see that, okay, that's not, there is nothing we can do about it, right? Okay. The popular choice hence is the rectified linear unit, which is nothing but ReLU, right? Switching from GPU to CPUs to GPUs with faster compilation time has also has made standard backward propagation feasible, where the cost of model is less. The point is that if it takes a long time to compute something, do it faster. Residual network can also avoid problems. It's a different class of neural networks, and the idea of residual network, I can tell you something like this. If you actually go to our network, this was our network, right? Where was our network? So this was our network, right? So basically, residual network idea is that you have done this transformation, and again, so for every transformation it is happening. So maybe in this layer, if this is residual, these weights will also come and join here. Okay, sorry. So this weights will also come and join here. This is an idea of a residual network, and there is a reason why we do it. We will not go to that, but there's the basic idea that you can also backtrack to and take the other weights, compute on every time step. Okay, they can also generally help to alleviate this vanishing gradient problem. Okay. The other part of vanishing gradient problem is exploding gradient. What is exploding gradient? It's the other way around. You have extremely large gradient. Okay. Like really large gradient, and result is an extreme large update. And how do you think that is possible? Let's go back to our equation of our weights, right? How do you think, where was the equation of this is very, right? So this is what, so you have W8 is suppose 10, right? W volt is 10, and this becomes 10,000, right? That is only possible because this is why it is this possible? This becomes also your gradients become extremely huge, right? And your updates are really large also in nature, right? If your updates, your gradients are very, very big, okay, your update might also turns out to be pretty big. That is also one of the problems. Now in really, really deep networks, okay, when the ResNet and started coming, right? ResNet, they were solving ImageNet problems in 2014, 12 onwards, right? And ResNet was like 152 layers, 200 layers or so, right? They've seen that because of this nature of ReLU, right? Sometimes, because this is unbounded, right? Here, this thing is unbounded. Layer after layer after layer, ReLU was giving, numbers which are really big, okay? And then which was actually transforming into large gradients, right? You got a really large gradient, and then then it was becoming like, you at some point of time it will become so large, maybe you'll overrun your floating point the buffer, right? It is also possible. So to alleviate that, there is also different versions of ReLU, but other than that, something else also you can do. Do you remember, to alleviate this, what we can do? If you have an exploding gradient problem, what can you do? Intuitively, we have done this actually yesterday. Sorry, last on Friday. If you have an extremely large number, suppose let's go back to our network, and this is our network. This was a small number, and this is a large number. Okay, I'm just giving you this two fact. What can you add here to ensure that this is you not regularize? What technically what can you add here? You can add something here so that it doesn't become very very big, right? Normalize, yes, exactly. How do you normalize? Absolutely. How do you normalize in a neural network? You have to normalize for each of the weights, right? Remember, you can add a layer called as batch normalizer, right? So batch normalizer is also a good way. Remember, if you add a batch normalization, so you can almost be sure that you can follow this Gaussian process of outputs which have some scale. It is not haywired. It's not really large. Gradients have somewhat acceptable limit, and then you can continue this idea everywhere. You can see this. You can see that whole thing, right? Regularization will allow you to do what? If you regularize, you will just only ensure that the overfitting doesn't happen. But you are not changing the number, right? Are you changing the number? What is one of the regularization thing is that you can use dropout. Dropout will say that, okay, fine, maybe this one will become 0, but this is still 10,000. This one still 10,000, but this is 0, but other two can be 10,000, right? But if you add a batch norm, you can ensure that numbers are in a acceptable zone, and generally it follows a unit Gaussian process, which means that your gradients or your these outputs are good. Why only do normalization process in input? Do it at every layer if you can. If you have really really deep layers, right? So that is the whole idea to it. Okay. There's also one more thing. In fact, this is like gradient clipping is a method where you can actually size the gradient. You will see that if you run with this, you will see that a loss will become nan. Okay, real time experience. Okay, anyone who has built any kind of network, you will see that nans is very common. NaN is like not a number because it's actually not zero. It's a large number. It's so large that it is uncomprehendable, right? That it has flown. So the loss will become nan. It's also a sign of exploding gradient. Okay, so you can do something called as a gradient clipping method to do that. Okay, so let's do one thing, guys. Let us go to our practice labs. I hope that so we can do. Let me just refresh my practice lab. So what we will do is this: we will actually, go through this new data set called as diabetes. Okay, we can run it via demo, or you can also run with me because I have already given that to you. So in a way, you can also run with me, but I would want you to pay attention as well, because what we will do is like we will try to build a network in such a way, in a step by step manner, in such a way that we add some intuition. Okay, hyperparameter tuning. If we will be using Keras, but Keras is just a framework. If you give it something, it will tell you an extremely large number of permutation combination. It will it will give you some results. But I want you to think that before you even do hyperparameter tuning, how can you think what is exactly happening? Okay, the network architecture is still belongs to you. You are the one who owns it, right? So even if you do hyperparameter tuning, you still have to own the rest of the things. Okay, so what we'll do is like we will do this diabetes.csv. Okay, this is a diabetes use case. So what it says is that the outcome is 0 and 1. It's a binary classification problem that you have a diabetes or not, given these 8 features. That's what we're talking about. Okay, given these 8 features, I think 7 features, 1 2 3 4 5 6 7 8. Given these 8 features, it will try to predict whether you have diabetes or not. Clear? Are you guys running this with me? Who all are running this with me or who are watching? Can I have some show of hands, please? Who all are running? Yeah, please, absolutely. Yeah, take 2 minutes, no worries. Actually, download it, take 2 minutes. Okay. What we will do, what we will attempt to do is that we will actually spend some time on this, and you will realize that the intuition works much better. Okay. So it's 8:50. I'll just start at 8:51. Okay. Um, right. Okay. Sorry, I'm just drinking some water. Let me actually start importing it here. Let me put the chat in this side, and it reads well. It reads well. Yeah. Okay. Okay. So are we in a position? Let's start then. I've just loaded the data called as diabetes.csv. It apparently has 9 features. One of them will be target, which is the outcome is nothing but target, and has 768 examples. Not a lot, but from our understanding standpoint, it is okay, right? And if we actually do a value count on my class, outcome in class, I can easily see 0 who doesn't have diabetes is 500, and 1 who has diabetes are 268. What do we call this? Do you see a pattern here? Do you see an issue, or is it okay with you? This is an imbalanced data, right? This is actually an imbalanced data, right? So let's see how neural network does. Okay, I don't know how it does. Probably it will not do good, but we'll see. Okay, we will. So if you have an imbalanced data, what are the steps that you can do to handle imbalanced data? Are we aware of the tricks we can use? We can use some sort of balancing action, SMOD or random sampling over. There are a lot of things here. SMOD is a very popular mechanism to handle an imbalanced data. However, SMOD might not work for images or language and so on and so forth, isn't it? SMOD is good for tabular data. So, and this is tabular data. SMOD should just work fine for us. Let us just quickly check whether we have any NA or not. We don't want any zero, null, and so on and so forth, right? It seems that it's a very clean data. It's imbalanced but clean, no null, right? Are you guys with me now? Okay, let's build our x and y. Okay, and let's build our x and y. So clearly, so what I'm going to do now is then I'm going to split my x and y. Oh, right, you are right. So aside the folder, and what I can also do is that I can, yeah. So let me know if so. But if I do this, then okay. So this is fine. Let me just actually increase this. Is this better? Yeah. Perfect. Thank you. Thanks for pointing it out. Yeah. So now what I'm going to do, I'm going to split x and y. I will split x and y in how many different data sets? Can anyone tell? You can see that I have split it into a train, a validation, and a test. Okay. Typically, why do we split into three? There are 3 types. Do we remember why do we split into 3 different data sets? Fundamentals of machine learning is this is the fundamentals, right? What do we do? Why do we do that? Such that I can pass my validation set to my cross validator. I can give my train to my learning algorithm, and I ensure that the data leak can never ever happen. Right? This is a very very important step. Okay, ensure that you always generally separate it out so that, and generally from X train we first split main X train X test, and then again pass the X train to split the xval, right? This is what it is. So at the end I see that my x10 train is 587 samples, xval validation set is 104. This is what I'll continue to give to my cross validator as a part of my fit process. Remember, keras.fit takes the validations, right? That's how I'll be able to plot it, isn't it? And my test, which we probably, I don't know, I don't remember we will use it or not, is of 77. More grants as in one more time, is it? As in like you want me to tell one more time, is it? Yeah, okay. So the reason, okay, why do we split in three different data sets? Because you don't want your data to be leaked to your model. You don't want the question paper to be shown to the shown to all of you, right? Then it's easy, right? So we will give the xtrain and xval. When you do cross validation, these two are extremely important. Once you do cross validation, right? Once you have the final model, you can then finally test your against your X test, right? This is going to be a truly new data, right? Model has never seen the X test. Even as part of the cross validation, it will be able to you will be able to judge whether the model is generalizing or not, right? This is fundamental of cross validation. As a part of your cross validation, you have to give xval, right? Remember that. Okay. No, we don't get two xtrain. Basically, the process is at the end we have one xtrain, one xval, one xtext, right? The reason I'm doing it is that I'm splitting. I have my x and y. I split into 90-10. I have got one set of x train and y train. From this x train, I will again split into my x train and x train and x val. From the first split, whatever the X test I have, I will keep it separate. Nobody has seen it ever. Remember that, okay? So as part of my cross validation, I will only use these two things: X train, X val, X train, X val, X train as well. At the end of everything, once I have a decent model, you are sort of confident. You're still not done, by the way. You can test it again, X state test. If it passes that criteria, then only it can go to production. Right, remember that generally there are two types of production thresholds, accuracy thresholds. Generally people will put, products will, teams will put. One is as part of your training process against xval. Once that is over, then your production at it as a X test, your xval threshold might be a little less, maybe 0.9, but your X test threshold might be higher. It has to work well in unknown, totally unknown. So X test is nothing but totally unknown. The model has literally never seen this, right? So this 77 samples, model will never be used ever. Okay, let's do some scaling. Why do we need to scale? We could have avoided scaling. Could we have avoided scaling? Could we have avoided scaling here? Any question? You can say that no, I can always as batch normalization, right? But I can always add batch normalization. My point is that I can always add batch normalization, right? Okay, let's go back. Can I add batch normalization? I can add batch normalization. We will be adding it. Let's look at this. Can I add a batch normalization here before this? Not possible, right? Batch normalization is a layer. It's a hidden layer. So at least I have to ensure that I will do scaling of my input value, and then I put it, and batch normalization is a hidden layer, right? So that's the reason I can't, let's do scaling. So that makes sense, right? At least do the scale. So let's do scaling, okay? So I have got my xtrain scale, xval scale, and xtail scale, right? Text scale. Everything is now correct. Let's build a model. Straight away, let's jump into the thing. Let's build my model. I will build what I will do. I will do sequential, right? So remember that my number of features are 8. So I will add an input layer. I will say whatever my shape is, right? And I'm replicating my model. This is sorry. So this is our layer. We had 3 layers. Remember, layer 1, layer 2, layer 3. I'm going to replicate exactly this one. Okay. Only thing is that the last layer I'm using sigmoid, not softmax. Okay. Okay. So where am I right now? This is self-learning. This is practice lab. So I have my input layer. Okay. I have 8 features. Remember, in your mind, just think about it. I have 8 features. First layer is of 64 units. Activation is with ReLU. It's a dense layer. second layer is same, 32 units, and third layer is 16. I will use sigmoid, but so that it will give me 0 and 1, right? Last layer of sigmoid is okay. It's a binary classification, 0 or 1. I can use sigmoid. I can use softmax also. Generally, I will always use softmax, but then it will give me a probability estimate, and then I will have to change something, right? So this is what I'll do. Summary, right? If I do summary, so I can see my, I can see my network. So it says that there are 3,800 and 201 total weights and biases that requires to be trained, right? Right. So now let's think about this question that if I have 8 features, how many coefficients will a logistic regression learn? If I have 8 features, how many? What will be the equation of the logistic regression? Or for that matter, what will be the total number of coefficients that that particular logistic regression model will learn? Perfect. Where is 9? No, 9, 9, 9, 8 plus 1. You are forgetting the C, right? Perfect. It's going to be 9. Remember? The C is there, right? The intercept is also there, right? Last C, which is nothing but also can be termed as bias. Remember that. So it's 9. So you can see, right, 9 versus 3002 to 3201, no comparison, right? So you are learning a lot of small things, literally small things, right? And this is what it is. You are learning so many small things, right? Okay. Now I'm gonna do something simple. I will simply add Adam 64, 32, and 16. That is correct right now. First 64, 32, 16. First layer has 8 features, right? Okay. So I'll do Adam. Let me just compile it. What happens when we do compile? Do we know what happens when we do compile? Why do this? Why do we trigger this compile? What happens when we do compile? When you do compile, this is what happens. Okay. You can see this computation graph. This is what is computed, and in the TensorFlow memory, there's something like this gets created. Okay, this is nothing but an auto differentiable function using a TensorFlow library called as gradient tape. Every node is nothing but differentiable on its own, right? And basically, this when you do compile, it creates this graph unit. Nothing else. But I am again, right? That is very important for you to understand what compile does. Okay, so I am using Adam, binary cross entropy, and accuracy. Perfect. I'm ready to fit. Let's train. So this is how I will do it, right? X train, X prime, and this is where I give my validation data. Perfect. Let me just run it. It should not take much time. I have just stopped the verbosity from 0 to 1 because it was just causing a lot of logs. Okay. Let's see. So it's done. I can see that it is done, right? This is what you can. So now let me do some Y train Y test, right? And I can also already do. No GPU. This is simple. No GPU. I don't need GPU. This is practice lab. Okay, I don't know what they're using. I can find out, but I don't think it is using any GPU. This is 768 data set. I don't think it requires GPU. It was running faster in my local machine. Okay, so let's do some confusion matrix. So do you remember how much data set that we are trying to? We were putting 587 data, right? And you can see my confusion matrix. The diagonals on these diagonals represents my true positive and true negative. Remember, right? They look something really fishy about it. Do you think what does it look like? We will come to know. Let's plot this graph now. This is nothing but a accuracy and validation graph. Given this graph, what do you say the state of my model is? Question to all of you. Are you able to understand this graph? This is nothing but number of epochs on the x-axis, and on my y-axis is the increasing loss. So the lowest is loss and the highest, so low to high. Is it underfit or overfit? Is it underfit or generally it's flipped? Okay, so it's overfit. Why it is overfit? Why do you think it is overfit? At this point, this is my test accuracy is gone down. and my train is going up, 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 right? This is a classic case of overfitting, and understandably, right? 3,200 neurons of 500 odd 600 500 odd data, right? Of course it's going to be overfitting, right? Because you have just too many things to learn, right? Like extremely small things to learn and extremely small data. Good. So I think this is a classic case of overfitting you found out. So let's do one thing. Let us add a dropout. So now, since we have found out overfitting, the normal process is that how do you fix overfit? I will simply add regularization parameter. How do you add a regularization parameter in neural network? If this is a classical machine learning problem, how do you, or what will you do? You will add a term to the loss function, right? Or you will use L1, L2, elastic net, whatnot. What they will do is like they will add something to the loss function. But in this case, we need to change our network model. How do we change our network model? We will add so we will add a dropout layer. For every such layer, we will say that 20% of neurons, please stop it. Right? So same thing. I'm going to have to rebuild the whole model. Right? So this is clear, right? So this started from here. For my 0th epoch, it started. At my very early, maybe like second epoch itself, training is my test is going down. Test has never gone above 0.8, but my blue line is training. Training is going up till 1, right? Whenever your training is going up and test doesn't follow the training, right? So you are continue to train. Basically, your training accuracy is going up. Your test accuracy is nowhere. So this is a classic overfitting case, right? Right? Where is this? No, so this is confusion matrix. This I wanted to show. I wanted to check that take only those y test which is more than 0.5. You can, you don't have to run the confusion matrix. So I wanted to say that. So this itself will give you 0.5. Anything above 0.5 is good, right? If you have anything above 0.5, that's what we generally consider, right? That if you have a value which is above probability of 0.5, you consider that as that particular class, right? So that's what it is. But if you actually plot the history, by the way, the fit model gives you what? Are we clear? It gives you a history, and history has everything, right? So that is what you get. So now what we are doing is that let's add dropout, okay? And if you add a dropout, what happens? And let's see. So what we did is that for every layer, for every hidden layer, we have added a dropout, okay? And this says my rate of dropout is 20%. 0.2 means 20%. So about 20% of neurons of each of this layer, right, will be switched off. So let's do this. So now we'll see that the model, this thing is changed. However, dropout does not contribute to any weights, right? So it does not contribute. My weight remains same. Let me run it again. And if I do the same epoch, same number of epochs, let it run. I'm just watching it here. This top corner where Python says the globe. So it's done. It says, and if I actually train this, it's actually a little bit improved, but the test is still. The test accuracy is still, I think the train has gone down. Clearly the train has gone down, but test is also, it's not, the difference is not that big. That is one thing is first. So dropout at such a small scale has given something. At least the gap between my train and test is not that large, right? Okay. So let us do one thing. Let us add a batch norm to this, okay? And see what happens. What we'll do is like after every dropout, we will add a batch norm. And it is possible that my numbers are, I need to add that, I've started with my original my original data set, I've scaled it, but I have not scaled each of my layer. Let me do that. So, right, I continue to maintain the same set number of units. And if I add this, now you will see that batch norm actually adds params, right? It's actually a learnable parameter, right? If you remember, right? So it will, now my things will shoot up by some 3600. There are some non-trainable parameters as well, okay? So now this is what it is. let me just now run this and see the same thing, right? Same exact same code and exact same piece. I don't know how let's see what it says. Okay, so my fit is still running. Okay, and see now it's much better. Train and test is at least there is some sort of inner synergy, right? Do you consider this to be better? Though the accuracy has gone down, overall accuracy has gone down, but your do you consider this as better? Why do you consider this as better? Can you verbalize it? What will you say if someone gives you this thing? It's like you're seeing that there is a very at least train and test is going in some way are almost are similar. The gap is much less. Okay, the at least one thing is clear. Will you say that this is a overfit model? It's no. So at least the problem of overfitting has somehow not, it's not there, right? Though of course the accuracy is not there. That is understandable because extremely we have a extremely small data set to consider start with. Because the accuracy results are convergent between training and test set, we can consider that the overfitting problem is sort of addressed. The model shows that it is no more overfitting. Perfect. Absolutely dead on. Great. Okay. So this is how you have to think. Okay, at every standpoint, this is how you have to think, and this is how you do it. Let us now what we have done. We have only used Adam, and we have not. So this is what I wanted to show you, that this is how you should do it. You have solved this problem of overfitting with such a small data itself. And if you give this with our linear regression, think about it: 9 coefficients, right? It will take a lot of time to even conclude, right? So let's lock down. So what we're saying that this is a good network backbone. So I will have 3 layers. Each layer have a dropout and a batch node, and this is a model that I locked down to do some more experimentations. And what are those experimentations? Let us look. I will now start looking at creating many optimizers. Okay, because there are a bunch of optimizers. Sorry, so with 8 features, we are taking units as, yeah, so no, 8 features is our in unit input is 8 features. And then for each of the hidden layer, first hidden layer there was 64 neurons, second hidden layers we have 32 neurons, and the third hidden layers is 16 neurons. Unit is nothing but number of neurons. How are we taking? Okay, how are we taking? We generally start with something, we start with these numbers like 256. There is no hard and fast. You can put any number. Okay, it doesn't have to be odd or even. You can put any number. What you want is that you want things to be representative in a way so that various corners of the data one should look at, right? So that's what it is. So how are we coming to 64, 32, 16 to start with is total guesswork. Let's consider that, and then we will see that we will try to optimize this. Okay, when we do we could have gone, absolutely we could have gone. Nothing, yeah, we can go with 100, 25, 25, no problem. There's nothing you can do about it. It's absolutely no problem. Generally, what you do is like you have a data set, right? Start with your hidden layers should have bigger as you go close to your last layer. Ensure that your layers are small. The units are small. Okay. Again, depends on the general problem. That's also not true if called images. But generally, you start with bigger layers, and then again you convolve, or basically you find a new hidden representation and make it small, and then you output it. But there is no logic of this to now. Our hyperparameter tuning only will actually tell us what is working out best. No. In our first layer means input layer. It's not considered as neuron, but input layer we are going 577 samples. Each of them has 8 features, right? Right. So there are. If you have to talk about neurons in our input layer, there are how many neurons? Guys, do we remember in our input layer how many neurons? No. Neurons, how many neurons? Not 8. Our features are 8. Remember? Okay. Don't know why I keep on getting. So our features are 8. Let's go back. Remember this, we discussed this, right? I should have actually used a, so in our case, this will confuse, right? So in our case, what do we have? Where, let's go back to our x. Where is our x? The representation of x. I have 587 samples. Each sample is of matrix of 8. So if you actually consider input layer as neuron, which you should not, there are actually 587 neurons in my first input layer, right? Each of the sample is one neuron, and that neuron is nothing but has 8 matrices. We don't consider the input layer as neurons. This is 587 is now mapped to 64. 64 is my first hidden layer, right? So that is what each column is considered as feature, right? No, yeah, each column. There are 8, right? There are 8 features, yes. Exactly. So let's, if you have to verbalize this, let's do this. Okay, one more time. So if you have 587 into 8, this is my input, right? This is my input which goes to my 64 neurons, right? And which goes to my, which goes to my 32 neurons, which goes to 16 neuron, and which goes to literally 1, right? 16 goes down to 1. So this is what is happening, right? In the first layer, we do not consider this as a neuron because this is X. So how many weights will be there on the first layer? Who can tell? We have gone through this. So there is how many weights? 5. No. Total number of weights are what? In the first layer, if I have 64 neurons, in my input layer, if there are 586 examples, so what will be the weight matrix of this? Perfect. 64 into 587. But we are still forgetting the bias. Remember that. Don't forget the bias. I think we have removed the bias out of our life itself. So don't forget the bias. There are some biases, okay? Yeah. So just consider that there are biases. So there are total number of weights we are talking about is 64 into 587, right? Something like that, right? So please be aware of that, right? Okay, let's come back. Let's come back and see that if we can handle, if we can, where are we? Let's look at some optimizers, which is fine. Let's look at optimizers. And what we've said is that this model is good, and we will lock down this model while we try to find out the best optimizer. Though we have used Adam, but we are not sure whether Adam is good or not. We will look at it. Okay. So I'll create a function on which basically does this. It's the same thing. If you call this function and then do summary, it will give you so many things, right? Now let's get some intuition what these numbers means. So what I wanted to show you is this, that when you create a model, right, any model, I think this is applicable. There's two things that I wanted to talk to you about. This is applicable, I think, in any machine learning model. Is that few things that you have to understand, or at least you can apply your intuition. Like say, suppose I have built this model, and I want to find out if the numbers make sense or not, right? What I'm going to do is that I'm going to use some SGD optimizer, and I'll do a very low learning rate. By default, if you use SGD, it uses a 0.1 learning rate. I've checked in Keras, okay? I wanted a very low learning rate and nothing else, okay? This is no momentum, nothing else. Normal vanilla stochastic gradient descent with a very extremely low learning rate. I wanted to actually not do regularization, but then I have to change this model to not remove the dropouts, which I did not do. Ideally, you should look at the vanilla model and run one epoch, literally one epoch, and check the value. Okay, if you check the value, you will see something. Okay, you just run one epoch and try to make sense of these values. Do you think you can make sense of these accuracies? Forget about the validation part, but can you make sense of this accuracy? Does this accuracy value make sense? And does this loss value make sense? What does this accuracy value says? That is 50%, right? Think about it. What does the accuracy value say? Does it say that it is 50% right now? In this one epoch, does it say that it is 50%? This model will produce, right? Now, how many classes you have? You have only one class, right? What is the probability if you put a blind and you dip into this 577 examples bucket, and what is the probability of picking one with diabetes or without diabetes? What is the default? Exactly. So think about that. This makes total sense, right? If you run one epoch, so for this you don't need any machine learning model, right? If you're talking about 50% accuracy, there is no machine learning model, because it is the by default. If you're just putting a blind thing, you close your eyes and put your hand and dip into 577. There's a 50% chance that one will be either diabetic or non-diabetic. So this is sort of matching. So your model layers are not that bad, right? It makes sense. That's what I'm trying to say. It just makes sense, right? Can we do some verbalization of this thing itself? 0.85. What is the loss value of 0.85? Can you make sense of this value itself? Now think of it, right? If I have two classes, right? And if you remember the binary cross entropy's formula, what was the formula of binary cross entropy? Negative loss of that predicted value. What is my predicted value? You just now said 0.5. Let me do negative 0.5 of log. You see that coming to 69, right? Somewhere close, right? It's not. This also generally makes sense. So now basically you can intuitively think that, okay, my model is at least not that bad. It is not bad than the worst. That is the normal general trend. Okay, a model now represents some sort of natural growth, right? Even if you don't have model, it will give you 0.5. Suppose if you have a model which gives you accuracy as 0.3, then you have to worry, because it's basically saying that your machine learning is actually bad than closing your eyes and dipping into that 577. So this is one way to look at. Just run one epoch and you will see that how good your model is. How your layers will tell you. If you use this model, the first model that we tried and run one epoch, you will see definitely lower accuracy. Okay, or maybe it's a higher accuracy itself, right? It is become biased towards something else, right? So definitely 0.5 will not be picked, right? The other thing, this I could not run. The other thing one should do, yeah, exactly. I mean, it's not. So basically, this is what I'm trying to say is that by default, you will anyway give a 50 percentile. Your model should by default, if you just run one epoch, it should give you that. That is your starting point. That will tell you whether the model architecture is representing of the natural order or not. You're trying to model everything of natural order, isn't it? So this can itself tell you that there is, at least you are in the right track. Some sort. If this is less or high, then there is a problem. Then you have to go back and say this model summary is not good. I need to do something else. This is not, whatever you do, there is some problem in this. So that is what I'm trying to say. The other thing that you have to do is, like, you should generally do, and this is important, is that take a very small subset of data, okay, and run a really large epoch. Take a like 20 subset. In this case, you anyway have small data, and try to overfit it. Your model must overfit. In this case, we started with the overfit model. So in any way it will overfit. But if you have a large data, are you able to overfit? This architecture of your model, is this architecture of your model able to overfit a small subset of data? If that is true, that will also validate the fact that your model architecture is good. It has good foundation. You can build on top of it. Because it means that it can learn things in a small subset of data really, really well. So that is what we want, right? And then anyway, when you add your dropouts and other things, or when you increase your epochs, or when you increase your larger number of data samples, anyway that number will come down, right? Because it will not be so much. But at least you know for sure that the model is overfitting. If you start with a small subset and model is not overfitting, you have a problem in your model architecture. These two things you can easily do to any machine learning model, just to gauge the, common sense approach, right? Before you actually do hyperparameter tuning. After any of these things, anyway, you have to, submit to hyperparameter tuning, isn't it? Which we haven't still come to, right? I think we'll continue this once post this as well, which is fine. I think it should not be a problem. So let's look at this. Now that we have we have gone through this, like lots of optimizers, phase that optimizers we haven't come that. Okay. So what we'll do is like we'll create a function. This is a function which takes a list of optimizers, create a model for that optimizer, okay, and plot the history. Okay. Let us run this. And then I have created a bunch of optimizers. There is a array of optimizers which is with all defaults, SGT default, SGT with momentum, everything default value from Keras. Okay, and then there is an optimizer with some sort of learning rate. Okay, some sort of values that I think are very appropriate. That's all it is, right? And then there is there are a bunch of other optimizer objects with an exponential decay learning rate. Okay, this is a function which Keras provides, where it will decay after so many number of steps. Automatically it will decay. Okay, and we can reduce this to suppose 10. Okay, and you can see that it will decay after so many number of steps. Okay, so I have 3 set of optimizers. So essentially I have 15 different optimizer objects of essentially vanilla stochastic gradient, SGT with momentum, SGT with momentum and stroke, RMS prof with momentum, okay, and and Adam. Okay, Adam has 3 things, right? A learning rate, a beta 1 and a beta 2. So I have done these things, right? So if I run this and I create my objects, so now what I can do is like I can, okay, I shouldn't have run it, but I can run this. I can pass with my optimizers with default, and it will run for each of those optimizers for each of those models. Let it run. In the meantime, we can actually let it run. So while it is running, let us look at this set of optimizers. Okay, and we can see that, right, that the model number 2, the optimizer number 2 was not that bad, right? What is optimizer number 2? Let's see what is my optimizer number 2. It looks like SGT with momentum and Nestrov is better. Adam is this last one. Adam is all over the place in this case, right? Adam is not at all, and this is representation of what we saw in our earlier. So in this case, this is a much clean graph, isn't it? Train base accuracy is so good. This is the best, right? And this is the best of lot. So I think SGT with, so now that is done. So here, optimizer with default, you can see with SGT there's little bit of gap here, significant gap here, right? Test is above, train is low. Not good, na? Train should be above, right? So this is again, so you can do these things, okay? So, and what I've done is that I have built 15 different optimizers with all its objects, and I have built it, and I can visually see, right? But then, how much you can, there's so much big landscape of things are there, right? So what we'll do is like, once we come back, so 9:30, right? It's almost 2 minutes to our break, at least in this part of the time world, right? What we'll do is like, so we will pause it now, okay? And we'll come back in 15 minutes, right? And then we'll finish our hyperparameter tuning. What I'm trying to tell you is that with these 15 different combinations of optimizers and so many different types of my network, right? It's really difficult for me to manually do this at all, right? To be sure that something is right. How do I know? How do I know that it is 30, 40 or not? So what we'll do is like, we will run our Keras tuner. Keras tuner is a package that is given by Keras to do hyperparameter tuning, and we can see that how we will do model building using that, and how we can trigger, how we can do hyperparameter tuning. Okay, does that work, guys? Let's come back in 15 minutes. Does that work? Shall we take a break, or do you guys do not want a break? Do you want to continue, or do you want a break? I am okay either way. Break, please. Yes, please. Okay, let's come back in 15, please. Thanks a lot. Thank you. Okay. Shall we resume? Great. Okay. So we have looked at some intuition of why do we know what sort of things that we can do. Let's now dive into this tool called as Keras Tuner. And if you want to see the Keras Tuner is here, right, somewhere. Yeah, this is Keras Tuner. Okay, this is quite a bit of documentation that you have. And basically, Keras Tuner on its own has a this thing. And I wanted to give you an reference of. So let me just first start with. So this is Keras Tuner. It has basically three types of getting started with Keras Tuner. Um, Three types of algorithms. Okay, one is it's a random search kind of which we will use now. And so one is random search. I just want to be absolutely sure what. So this is one is random search. Okay. Another is a Bayesian optimization technique. It's nothing but a you can consider this as a similar to you have done the naive Bayes classification, right? Um, no, it doesn't. Just upgrade the PIP. It will not upgrade. It just upgrades the PIP. So Bayes optimizer in Keras Tuner, what it does is that it updates it uses a Bayes algorithm, prior and post, to predict the the hyperparameter space. But fundamentally, if you understand what is hyperparameter, now that you have gone through so many things, right? It's like how do we know, in this hyperparameter space, how do we know which value is right? There's just so many tons of numbers, right? These are all numbers. 0.89. So momentum, the documentation says that you should use 0.09. But what about my learning rate? What about my beta 1, beta 2 for Adam? Right? There is no set values for these things, right? So best is to run via lots and lots of trials. Okay, we run it in a loop in such a way that we test all of these things. Again, for every such combination of it, we will create a model, and the model will be running its fit process against a validation rule, right? That will be recorded. Let me just go back to Keras Tuner. So that will be recorded, and at the end you return things back. So if we have to just give you a context on what is hyperparameter tuning, I think that will actually be good, right? To get a little bit of context, right? So where are we? Yeah, so this is hyperparameter tuning. What is hyperparameter tuning? Parameters are found in lots of places, not only in neural network, in all the places, right? So these are the various important learning parameters that we have. We already know what is mini batch size. We said that it is 16 in our case, right? Number of epochs 100. How do you know we have to train for 100 times? Why not 200 times? How do you know what are the number of hidden units? Classical questions, right? You can use 125 for 25. Yes, you can. So what is the right number is not known. So that space of hyperparameter is extremely large. And choosing this subset of optimum hyperparameter itself is the tuning process, right? And we need help. We need lot of help. So, and this libraries, what they do is like they provide that help to us. It is not physically possible for us. If you remember, in classical machine learning, you have what do we have? Grid search CV. The whole objective of cross validation was one of the reason why we used to do cross validation is to actually tune this hyperparameter, right? Effectively. So we have grid search CV, we have random search CV, we have hyperopt, we have Optuna, right? I have shown you guys, right? So did I show you guys? I think I've shown you guys, right? No? Have I spoke about Optuna or no? I don't think so. I don't think so. So we have Optuna, we have HyperOpt, various types of these libraries which helps us to do that. Optuna is a very popular library. Okay, if you actually go through it, what does Optuna does is it also if you actually see Optuna, right? It will yeah, so you can read this reward. I wanted to actually show you the Optuna's. Yeah, so this is a hyperparameter optimization framework itself, right? So you can simply install, and if you actually see TensorFlow documentation, it's fairly simple, right? It's almost like what Keras Tuner is giving you. It basically considers every trial, okay? It's nothing but a trial and a study kind of a thing. You can create a study, and it will do the trial, record all those observations, right? And then you can use that to tune your final model, right? Because the space of hyperparameter itself is really large, and there is no clear-cut way to handle it. And Optuna, what it does is it has the deep integration with TensorFlow, sklearn, and all the other various frameworks of machine learning, PyTorch, right? Chainer, Keras, and it can actually integrate very easily, like extremely simple. You don't have to do it. Similarly, we are showing you right now. We will show you. Let's go back to the code and see how we can use this Keras tuner. How easy it is to use this Keras tuner to run our model inside and find out what could be the best hyperparameter. So what are we going to do? We will still take the base architecture, that the architecture that we have said, right? That we will choose a dense layer, a dropout, and a batch norm. Only thing that we will try to do here is that if you notice this, right, these are the things that what I'm saying here is that the units in my dense layer is actually something like this. HP is nothing but HP will be a hyperparameter space, okay, of KT. KT is nothing but Keras tuner, and the API is like this. You can specify that this is going to be an int value whose minimum will be 32, maximum can be 1024. And I can say that step size is 16, which means that the trial will be run for every step size of 32. 32 plus next one will be 16, and the max value will be 1024. Okay. Are you guys with me? You understood that how to actually give a really large, start and end or min and max kind of a thing for an int using Keras tuner. So you see this. This is what the unit, the conundrum that we were discussing in the initial, that how do I choose 32? We don't know how to choose 32, right? It can be anything between 32 or whatever. So what I've done is now using the hyperparameter tuner from Keras, right, which is called as Keras tuner, you can specify something like this. Okay, what effectively it means is that this could be a value between 32 and 1024. So when it runs its own trial, it will try various such values between 32 to 1024 for the hidden layers dense unit at every jump of 16, and it will assign that value to this guy, to this unit, for every such combination permutation, right? It will also, you can also specify, you will also specify that activation can be a choice between ReLU and TANH. It's typical thing, right? We know that we will not be using TANH. We might use a leaky ReLU or PReLU or something like that. But just wanted to show you that. Are you guys able to understand this line? This is important. That's about it. I mean, so this just does it. No, this is, we are not training. Okay, so this is basically what are we trying to do? Of course, our objective now is to find the best hyperparameter. This will take some time because it's going to run a lots of trials. Okay, in this case, I have only asked it to run 3 trials, but generally you will be running hundreds of trials. This phase of, you know, this phase of this any data science project takes time because not only your training is, you are going to run a lot of times. You will be running training many times, by the way, not only one training. You will be training multiple times for each variation of these hyperparameters that we will discuss. So like for unit between this to this, activation between this to this, that is for only for the first layer. I have my second layer in my dropout. How do you know that point 2? Not, right? You don't know that, right? It's a float value. So I've said that between 0.1 and 0.54, there are 3 places, right? So try all of them and report it back to me. So this is how you actually specify. So in your model architecture, you make these tweaks in your build HPT model function. Okay, this is just a code that I've copied directly from the Keras Tuners API page itself, and I'm just showing that to you. Okay, so it's nothing proprietary or anything. This is the standard way to do it. There are other ways, other better ways where you can actually implement the hyper model of Keras Tuner, little advanced way, and software engineers will resonate with it because there's a lot of places we would need hyperparameter tuning. Okay, it is not just these things. Okay, so you would need a proper framework to actually even do this itself. Okay, but the crux of the matter is that the same network, each and every hyperparameter, we have now run it via an HP dot either a float or a int or a choice kind of an object where it gives me an options to each of these things, and I build this model, and even if you see, right, I have added the model. This there is no hyperparameter tuning here because I know that my unit will only be one. However, in case of my learning model, right, my LR can be of max like this is the 10 no 004 to 002, right, 0.0042 to like 10 to the power minus 4 to 10 to the power minus 2, right, a very small learning rate to a reasonably okay learning rate, right? I want to try all of them. In fact, what I wanted to do is like I want to try all the optimizers, all the 15 optimizers that I've chosen with all the various learning rates, and that is what you will give it, and that is what it will try all of them, right? So this is a function that you have to do, okay, and where each of this hyperparameter you need to wrap it under an hp.int or an hp.float or a choice kind of a wrapper. What it gives you is a range, right? Once you have that, your basic model is updated with hyperparameter tuned. It's not done yet, okay? So but did you understand that how did we change the model to find what is the right hyperparameter? This is a step one. The second step is to call this function and with kt.hyperparameters, right? Okay, this is my step 2, and then I build a tuner class. So again, as I was saying, if you actually go to Keras has 3 tuners: random search, Bayesian optimizers, okay, which uses a naive Bayes algorithm, a Bayes algorithm. Yeah, those are just names. Okay, I'll come back to that. Those are just names. So this is rate 1 because this will tell me to that which ultimately it will go here, but this will tell me, I'll show you, this will tell me that which hyperparameter's value is rate 3 is. So rate 3 means essentially the third layer's dropout value. Unit 3 means the third layer's unit. Because if I make all of them same, right, they will override each other, and they will go and your unit 1, the first layer unit will be same, the second layer unit will be same, third layer unit will be same. It's considered them as variables internally, right? Ultimately, it's basically these are nothing but variables which indicates which layer they belong to. Okay. Finishing upon Keras also has a third hyperparameter tuner, which is called as hyperband. Okay, if you actually look at hyperband's documentation, and I don't know where it is, so we can actually look at is that this uses an algorithm called as bandit, okay, hyperband, which is a part which is done in this thing, reinforcement learning. Okay, this is an RL algorithm. Okay, and it uses an objective on RL, like an agent based network, to learn the hyperparameter, right? This is actually a pretty sophisticated algorithm, and if I'm not wrong, it's fairly used a lot of places, right? Optuna, on the other hand, if you see Optuna, right, it has, the algorithms are not listed, so I don't. So I think it only has a naive-based algorithm, a Bayesian-based approach. Let me just look at the key features. eGOT search space. Yeah, I don't remember what was the algorithm that it uses, but it also uses something similar, but with its own implementation. Okay, there are a lot many. I will actually show you. Let's go with Keras tuner and finish this thing, and then we'll see that how there are others also, right? HyperOpt also is there, but HyperOpt generally doesn't work well with NN networks. Okay, so this is what we do. Now what we'll do is like we'll create a tuner object. How do we create a tuner object? Choose your tuner, give the function definition, that is build HPT model, give it an objective which is the validation accuracy. You don't want it against train, right? You want it against validation accuracy. You set the number of trials. This is never 3. In real life, it will be much, much more, right? And you can say that per executions per trial can be 2. Do you want to overwrite things? And where do you want to save? We don't need these things, but where do you want to save? All these things can also be reported to your model serving infrastructure, and you can have a live hyperparameter tuning at a really scale that is unprecedented, right? So if you actually do this, the tuner object will be created, and tuner object can actually tell you the search space summary. Right? Let's just run this. It's fairly simple. It tells you that there are default search space size of 10, and this unit 1 is nothing but this, unit 2 is this, right? In unit 1 is this, activation is this, unit 2 is this, activation 2 is this, rate 2 is this, rate 1 is this, and it's going to take a combination of all of these things randomly, by the way. Okay, so and try to find out what is your it will still not run the train process, right? So what you do is like after this, the tuner.search, and at that time you have to give it the test set, the validation set, of course the test train set, and the validation set, and say that for every such trial, how many epochs you want to run, right? So for every such trial, how many epochs will you run? So in this case, we have set 3, right? So if you run this, so for trial 1, it is running 10 epochs. Again, then it's continue to run, right? Then trial 2 starts, it will run so many things, right? I run trial 3, and it will report back. So that is where it will end. So it says that trial 3 is complete. Looks like I have some sort of my best validation accuracy so far is 0.80. Okay, so this is what it got. Okay, and it records all the things. You can get the best parameter. Okay, if you get the get parameter, you can see that the first unit, it's saying that the first layer should be of unit 800. We said 64, remember, right? And the activation should be 10H, rate should be 0.2. The second dense layer should have 112. Okay, so to reach this number, and activation should be ReLU, okay, and rate should be 0.3, and this large thing is basically 0.3, and so on and so forth. So this is, and it also says that the learning rate should be somewhere here. It's almost impossible for us to even imagine these numbers, right? So it finds out in a way, it's just does a random search to find out what is your best hyperparameter. You take these numbers, right? You can also get the model. What it does is that it saves the model also, right? It will store all the models. For every run that it does in the search, where did it do? The search, it will save the model. Okay? It will store the model because running this might be computationally pretty intensive, isn't it? So it will store the model, it will give you the best model, and if you want, you can actually see now the best model. So model 0, you can ask that give me all the best model. How many models? Top 2 models. And if you are on that top model, if you look at the 0th one, which is the top one, you will see that it has cranked up to some 100,000 weights, because your input neurons have increased drastically, isn't it? Dramatically they have increased as per the tuner, right? And if you take this in the hope that so just don't take it on its face value, still take this, evaluate whether this makes sense or not, okay? And then if it does make sense, build the final model with this, and maybe you now have some sort of guidance that okay, looks like to achieve my rate of accuracy, the validation accuracy of 0.8, I have to use this model which has been found using a randomly searching my these 10 different parameters, right? Various 10 different parameters, and you can continue to add more parameters, right? I could have easily added more SGT or different types of optimizers also, and so on and so forth, right? So this is at its core is fun, hyperparameter tuning. After this, does this tuner, why will the tuner lead to overfitting? Now, so are you saying that if the tuner gives a prediction like this, will it lead to overfitting? Is that what you're saying? That if I take this model, yeah. So you remember what is that you have got the best parameter. What is the next step that you should do? You should immediately take this and apply in your test. Remember the very first time we have separated the test as a part of, we have created xtrain, xval and xtest. Immediately take this and put it on the test. You will find out the test accuracy, right? But that will easily tell you that whether it is overfit or not. If your test accuracy on that x underscore test, we have not at all used x underscore test anywhere. It crosses the threshold that you have put, then I think you are good, right? Because that is one data set it has never seen, this model ever, right? In any of its cross validation, it has never seen. That is as new to him as with any new data. If that crosses, so if there is a low accuracy of that, you will immediately see that okay, clearly this model might have been overfitted, okay, for whatever reason, whatever it is definitely not working in live production. That is where you take this, run it again, test whatever the business threshold that you have put against the test. If it crosses, it's okay to deploy to production, because now that you have some sort of science behind finding this number instead of randomly going through it. Now know that something you have done in a way, and you can also use this the hyperband. The hyperband is a reinforcement learning based technique to find this, right, across the search space. And you can use complicated algorithms like that to find what it is. So that is in a crux is what hyperparameter tuning is all about. And Optuna, Keras tuner, they're all good. Keras tuner also, if you know what is tensor board is you should know. I'll send you the links. Tensor board is nothing but a model server infrastructure. These are not done in notebooks, right? They are live. They're every time you're updating something, it goes to a web page, and you can track all those things. Just like the way we track, we just like the way we track, matrices, right? Live logs. How many customers are logging in a website? There are ML ops, machine learning ops, right, at scale, which tracks all these things at each level, right? And as much as of metrics that you can gather, it's better for you, so that you don't have to, you have clear visibility. If you go to this website, it's called as Weights and Biases. Have you gone to this website? Do you guys know about this website? There are many like this, okay? It's not just this. So you can look at this Weights and Biases, or you can publish your hyperparameter tuning and at scale, and persist it, and over the period of time you can run experiments, you can generate reports, and you can do a lot of things. It also gives you interactive visualization, and at scale, right, when training a model is cost, right? If you are training a really large network with millions of parameters, you can imagine the amount of cost that you have to incur. And hyperparameter tuning is on an extremely large this thing will be costly. So you are the one who will be actually asked that how, okay, I have spent so much dollars, what's the result? This is the result. Why the result? This is the why is the result. You can have a clear visibility. Not only that, you can also find out issues in your Weights and Biases is pretty good. It's a very popular platform, MLOps platform to do that. TensorBoard is also open source, but it's also really good. And there are many. AWS also has, right, something called a SageMaker. Azure has on its own. then you have a bunch of them, right? All of them are equally good, right? So like if you see, right, Optuna can publish directly to weights and biases, right? So you can do this and just it will directly publish to weights and your instance of weights and biases, and you can know, right? Because these trainings, right now we are running trainings in like what, minutes. Trainings will not run in minutes, isn't it? Training might take hours, and if you are really in a production ready system. So these are the things that you have available with you, right? So the other sort of things is that if you see hyperopt, right? Hyperopt was a good thing. It also uses a Bayesian optimization algorithm. It was okay to some extent, and it uses three different types of algorithms. You can store all those things, but I'm not sure actually how effective it is on the neural network side of things. Uh, in a sense that it doesn't matter. This also has a similar notation of HP dot choice and so on and so forth, right? But I think, yeah, I think it doesn't matter. But thing is that this new age Keras tuner and Optuna, they can publish to this MLOps environment, which is cool. You don't have to worry. You have to worry the one thing less about it. Okay, that is our hyperparameter tuning. Okay. Any obvious questions before we move to interpretability? What we'll do is like we'll finish this lab, and then we'll see if there is anything theoretical that we have to discuss from the presentation. I really wanted to actually start up computer vision, but let's see whether we can do it or we can do it tomorrow also. It's not a problem. Okay. Um, okay. Any obvious questions? Any questions on hyperparameter tuning? Anything that we are you want me to repeat? Okay. Fair enough. So shall we start interpretability? So what is interpretability? Let's look at the let's look at um, you know where is interpretability? So it's basically interpretability is the degree of human's ability to predict a model's result consistently, right? Now that you are saying that you are doing 0.8, how what do you mean by 0.8? I mean, how can you even say that it is, what does it mean something or not? Is it a fair, so you can actually, evaluate if it is the interpretability is fair or not. Does it cause any privacy concerns? I have discussed in the initial parts of things that large AI models might cause really big problems, isn't it? It might can learn a lot of things about you, can become too biased as well, right? So, are you ensuring that there is privacy? Is there reliability? Is there a trust issue for medical field, right? Can you be confident? How can you be so confident? In finance, you have not given someone loan. Can you tell that why have you not given a loan to this particular person? Or can you tell why have you not given loan to this group of person? Right? Both are equally important, right? Just like so, interpretability is pretty big. Okay, we focus a lot on algorithms, the learning algorithms, and all other things, but truly, like if you have to really think about putting all these things into production, if you cannot answer the question that why a loan is rejected for this particular person, you probably whatever you do, you will might not be able to put this thing to right into production. If you cannot answer in deterministically way that how sure are you that someone has diabetes, how sure are you that someone has a problem with someone has a cancer, right? Given XYZ features or images or whatnot, right? So these are very high critical cases, isn't it? So, so it is important for us to understand why interpret it. It's basically for some reason we don't focus on that. Is we means like from a teaching standpoint, but it's a extremely deep topic. Lots and lots of. If you just go to archives, yeah, I think you just go to archive. Do you guys go here? If you don't, I think you should start going because it's a place you will see that. So just type XAI, okay, and you will see that all kinds of human-centric papers have started coming, right? All are new, casual, like extremely large and explainable AI systems, okay. Started. You have lots and lots of papers. People, this is a very active form of research, which requires lot of effort. Just so when it is not needed, when it is an insignificant model, right? And we are not talking about insignificant model. When something is really well researched, right? For scenarios where people or more program has of nefarious intentions, right? You are creating a machine learning model which does harm, interpretability might not be needed. But I'm assuming that we are learning all these things for the greater good of mankind and the whole earth. Why only mankind? So, it's important that we actually understand this. There's broadly two types of interpretability, intrinsic and model specific or model agnostic, right? So the theory part says that that we have you can achieve interpretably by simply applying the model and analysis after the training is over. So once the training is over, whatever you have trained, right? Sorry, whatever you have trained, whatever you have trained. So this is what it is, right? After the training is over, you can analyze it, and lot of tools have been built on top of that, right? And this also the intrinsic style of XAI refers to mostly simple structure. You are doing linear regression, 9 weights, okay, 100,000 weights. Can you even think that will you be able to explain that why that particular 50,000th weight is a point 0.2 value which might be causing something else? That is really difficult, right? That's not easy. We also have model specific and model agnostic. This framework that has been built, you will see that TensorFlow has its own structure, something else has its own structure, or the model type of model that you're using. For vision, you are using CNN, it uses its own interpretable systems. So those kind of things are also there. So, but there are cases where it's totally model agnostic. You give it any framework or any types of model, you will be able to build something out of it, right? Or there are work that only works on features, based on the features input and output. Like you get a feature and then your output, which is sort of confusion matrix, right? Confusion matrix only work on your last results. Doesn't matter what you do. Feature importance, you see that if you run random forest dot feature importance, it gives you after the model has been built, right? Okay, so scope of interpretability is pretty large. You have to provide algorithmic transparency. Okay, a company who is trying to get acquired, right, has to explain how your algorithm is going to do. Okay, it also has to be global. Global interpretability on a modular level is very important. Okay, are you able to explain for the whole population? Are you able to explain for the type of a population, or are you able to explain at an one example level? Can you tell me why that particular person you have not given loan, or can you tell me why this group of person that you have not given loan, right? So these kind of things are pretty large. So let's do one thing. Let's quickly go through this, okay? And for that we generally use Lime and SHAP, okay? So Lime is also I will actually show you a paper. This is I think this year's paper itself. Let me show you when you can see this, right? Literally 28th of June. Okay, so this was from Salesforce, if I'm not wrong. Okay, yeah, this is from Salesforce Research. So what they are saying is that, and not everything has to be true, but there is no reason why it is not right as well. So every research paper has its own pluses and minuses. The plus here is that it, for us, for in this audience, we can find out what are the various types of interpretable framework that is existing out of it, at least some glance of it, right? Or we can also find out what are the different methods or interpretability algorithm that we have. We have so many interpretable algorithms, right? Lime and SHAP is also a black box types. Okay, it works fine. Lime is neural network model. Lime, I'm not sure. Image definitely Lime will not work. Okay, it's Lime and SHAP are both are methods. Okay, I was able to run Lime SHAP for some reason. Lime in on my in that particular practice lab is not working. I will try in Google Colab and I'll probably share that with you. But so what this particular research says that OmniXI is something that they have created. Let me find out that. So I think, yeah, this is the one. Okay, the GitHub star is around 300, so it's not that. And I think given the fact that it's just been recently launched. So what they are saying is that they can do a lot of things. It's an open and interpretable, explainable AI format. Okay, and it can do so many things. It can do one explainable framework can do EDA, tabular, image, text, time series. It's not bad, and even support torch. So I'll show you what is integrated gradient. So torch or TF as well, right? So the other things that we have this interpretable ML. So there are many frameworks. Eli5 something is, I don't know whether you should know it or not. At least in machine learning, what you should know. Eli5 says that explain like I am five, right? So that was very popular initially. But let's just go to the practice labs. So what I'm gonna do is like you have to install SHAP, right? Import SHAP, give the model. So the same model which worked given our hyperparameter, right? That is what I've given. I did not build anything else, right? And I've created an objective. This is, I think, called as an explainer, right? An explainer object, right? And given an explainer, and this took some time. What it is telling me is that you know for for the prediction that it's been seeing, right, these features are more important, which is obvious, right? So if your glucose level is high, so this is class 0, which means no, right? And you can actually change all those things. There are multiple types of statistics you can generate, and you can actually show all those things while you are trying to explain what is going on. Now this kind of a statistics is an overall stuff, right? You can go down to each. If someone asks that why is this customer ID 1234, why the loan was not approved, you should be able to go down to one level and say that, right? Now similarly, if you actually go to this paper, right? I think so. This paper is also came in March. This someone told me that this paper is good if you can read this. A lot of it talks about lot of things on explainable AI itself. Google has this thing called as integrated gradients. Okay, it's a beautiful tool focusing on how the gradients change, and there a lot of work is going on. Extremely active area. Okay, there's not one tool again like anything else. Not one tool. It's a lot of tool. So integrated gradient works on those gradients which come back. Okay, and it basically does a what it does is that you can actually go through this. Okay, this is again TensorFlow tutorial interpretability. It's a big section on interpretability under TensorFlow itself, right? And there is a run in Google Colab also. You can run it easily, right? And you can upload your model, and it can show you that how much interpreted it is. In this particular model, it is using a model. An image classification model, famous one called as Inception from Google itself, which has like many layers. You can see that, right? The 6 million. This is 6 million parameters layer, right? This is basically compressed into one layer itself, and this is what they were trying to interpret what was happening in this layer. Okay, at least in this Google Colab. Pretty interesting, right? You should be any what good thing about TensorFlow is that they give a lot of code. You can click on it, it opens the Google Colab itself, and you can run it directly from there. Okay, You might able to download notebook, but no point because you need little bit of compute, right? And Google Colab might give you a little compute. Okay. Integrated gradient is a good one. There is one more tool from TensorFlow called as what if tool. Okay, and what if is basically it provides to understand again same idea, expanding understanding of a black box model using both classification and regression model. When the moment you say black box, it's generally been referred to as, in this case, it's neural network. And you will see that there are TensorFlow notebooks. So it's not one thing, okay? And what if tool with, the code is very simple actually. Anyone can integrate it. I was seeing the code, and you can actually put directly into the TensorFlow serving model. Whatever you people have done for weights and biases, you can build on your own without spending a dime. Okay, and all you need is engineering bandwidth to build this infrastructure. But it is pretty nice. If you actually go to the What If Tools website, it looks something like this. Okay, it has a ready-made integration with Jupyter, Cloud AI, TensorBoard, and other things as well, right? The code looks very simple. I will wanted to show you the code. I don't know. I saw it somewhere. It is just one line of code to integrate things. Okay, so I think the video was showing it, right? Lot of active research, lot of things. It's not, I would suggest that if you want to start doing something, start with integrated gradients and TensorBoard, okay? Or I have seen a lot of people in production weights and biases because they're just, it's a ready-made platform, okay? People with really proper proper ML and AI teams, right? They will just use weights and biases or something equivalent to go with it, right? So this is something that we spoke about. There's one more, yeah. So I'll send this links, okay? So I'll send this links. Check this GitHub, okay? This is awesome machine learning interpretability. There's a bunch of resources on interpretability. In fact, there are browser based, where you can simply upload the model and explain and ask a question. It will do that. There are also fairness indicators. Okay, fairness. You should know that this fair learn, right? What is this fair learn? From fair learn is from whom? I think it's from Microsoft. So the idea is how do you improve fairness in AI system? First of all, for that to know, you have to ensure that you understand the model. So this is also a part of explainable system. This is what I was talking about, right? Are you are you not giving loans to a certain type of community, right? Because of your affluence or your arrogance or whatnot, right? Human beings can do that. How will you hold a AI system? So this use case is exactly about that, right? Credit card loans, right? To a non-privileged or maybe some sort of racial dispute. And AI systems learn it, right, from real life biases. So you should see that there's a lot and lots of active work going on, and very very interesting area. Nascent but very interesting area. What is happening is that it's been now modeled under, if you are building really things on TensorFlow, you generally will probably use TensorBoard or something similar, and then all the tools are there, and start using them as it is. So that is what we have. Okay. So that sort of completes our understanding of everything about neural network to start with. Let's revisit what did we do. Okay. We have discussed a lot till lesson 5. I think base of neural network is, you have now the base of neural network, everything ready. I wanted to, so basically we have discussed 4 lessons. Forget about lesson 1. So 4 lessons: AI, ANN, neural network tools and frameworks. We will stick with Keras and TensorFlow, right? and we've seen that. So we'll start this, but doesn't have to. We'll start something. We'll start in CNN today. At least the intuition. We've looked into the details of each of those things in depth, right? I think we are now pretty much okay to understand where we want to go, right? At this point, I think you should also do is that if you actually go to the assessment, let me just go to the assessment. Have you actually started looking at the projects that that's there? Now, I don't know what is there in your LMS. Maybe do you want to check right now what is there in your LMS? I can see these things. I don't know whether this is the same one that you are watching or not. Can you guys see the same one? See, housing data analysis, lending club loan data, and pet classification, right? Same one, right? I think you are now well equipped to start at least housing loan data analysis and lending club loan data analysis. These two you should start. Okay. And what we can do is like, because pet classification, maybe what you can do is like, maybe let's finish CNN and start at that. If you already know CNN, you can start on this. No. We will anyway be scratching a base of CNN. We were not going to go deep because there's a separate course for that, right? Our scope doesn't allow that. But I think you should start looking at housing data analysis on its entirety, and on a daily basis, maybe from tomorrow onwards, start asking me questions in whatever way I can help you. We can do this thing, okay? This is going to be a pretty, if I'm not wrong, I have not seen the data set, but this housing loan data analysis might be a pretty involved exercise. You have to do a lot of things, right? Look, load data, check narrow. So you do have EDA, balance imbalance handling, do it properly, calculate sensitivity. Also, this is all about, this is non AI. This is just, you don't have to create any model. Okay, I don't know. I think you don't have to create any model here. It is just only perform data processing and build. Sorry, you do have to build a deep learning model, right? So this is the tabular data, right? So you should be able to start on this. The lending club this thing has a quite a at least more features than this, and this task is also there. You should be able to download the data set. You have to do EDA, do proper EDA, do feature engineering if you can on us, and then build a proper neural network. Okay, do hyperparameter tuning, and then do everything essentially, and also end with some sort of explainability. This project 1 and project 2, I think we should start at least thinking about it. How do you want to do it? This is one thing that I wanted to tell you guys. I think you're equipped, more than equipped with to start this. Okay, are we on the same page, guys? Okay, awesome. This is also a practice project. I don't know if you have taken this or not. I think that you should do this. It will be good. So this is a PUBG game that has enjoyed massive. Okay, so okay, and then quite a bit of this thing. So this is the win place prediction. The target is this, and quite a bit of features. And this will be a good exercise, right? To do a practice on. Okay. Awesome. Great. Shall we start CNN a little bit? Just a little bit, and then we will anyway, take it up with these things, right? So we are okay, right? So you guys are okay now with your now neural network trained. Okay. So let's do one thing. Let's start the basics of CNN. Okay. What is this? What is this thing about CNN, and why do we have to worry about this convolution neural net? Okay. At least let's give it an intro. Let's spend about 10-15 minutes, not max. And then anyway, we'll do it tomorrow in its appropriateness, right? So what is CNN? So at the end of this particular lesson, so this is lesson number 6. What we are pending is like lesson 6, 7, and 8. We have a lot of time. We can go down to each of those things and in detail. It's not a problem. Okay. And whatever we learned. So what we'll do is like we'll implement a CNN architecture. We'll see what is CNN first. What is a C in NN? Okay. Till now it was ANN, and then earlier then before that it was NN, and now you are adding a C. So the only the thing is that missing, you also have DNN, deep neural network. So what is missing is now C. I don't know whether we have B or not. You can also create a B. So why? So what is this C? We will see that. But first understand that what is why. Let's discuss on the why part of it, right? So one thing it was very clear as we discussed initially, right? The vision, intelligence. We are in the business of modeling intelligence. So two critical part was to model vision, model language, right? And modeling vision can be perceived like this, right? So like you have your brain and you have your visual cortex somewhere, right? And it's neurologically, people have said that the idea of CNN was motivated from neurologically, and to find that locally sensitive and orientation selective nerve cell. Essentially, we can predict that, we can see what are faces and objects. It's easy for us to find out edges and lines, right? We can detect shapes, right? We can find receptive fields, isn't it? And we can find commonalities between it. Things which moves are generally called as vehicles. There is a generic understanding that things which moves are vehicles, at least artificial things which generally move. And then inside the vehicles, we will have different types of vehicles itself. So there is no difficulty for us to actually say, classify between a car and a bus. But that and it becomes easier because there is a common knowledge or general knowledge in our brain so that is also moving. There are some sort of common structure, right? So CNN, inventors of CNN, who is the inventor of CNN? We'll look into that. You already know that person. So inventor of CNN designed the network in such a way to extract relevant features, right? Extracting relevant features is a very, very important step in neural network, and that flavor continues. However, to extract features from what you are seeing is not as easy as of extracting a feature from a tabular data, because the data itself is complicated, data itself is fairly unstructured. CNN was actually invented by Yann LeCun. Yann LeCun is Facebook's chief AI, and he's one of the father of deep neural network as well, right? You have seen his work many places. But in 95 or so, he introduced this idea of CNN. Okay, what is the basic idea? The basic idea is very simple. Each represents that local. There are three fundamental core ideas behind CNN, and we will discuss this again. So don't worry. I'm just going to set up the context so that we will have a deeper discussion on CNN itself, right? We will see that why do we need this and so on and so forth. But so what is the local connection? Local connections are nothing but, so images have local connections, right? In a particular image, a house is, it might have many objects, but if you're trying to look at the house in the image, instead of the trees which are on the left side, right, and the house on the right side, you will not be looking at the whole image. So there are some sort of intrinsic spatial, spatialness in terms of localization, right? The local aspect which has to be represented in the feature. It's not that easy to represent out in features, right? So how do we get that local connections out in the network, or in other ways, we know what is the output of each layer, right? That is in the numbers, right? Each of the hidden numbers is what we can refer as a local connection. What is layering? This is what I was talking about. If you can find out, if one layer can detect face, one layer can detect, cars, another layer can detect type of animals, right? Then you can represent hierarchy in the features. This is important, right? This is something that we do. So you have these boundaries. It goes via some other. So this is one layer. This is the output of one layer, which are nothing but something, which are nothing but numbers, right? But it can be put, if you can plot this thing, and then it goes via one more, activation plus one more summarization plus activation and one more layer, and the output might be the eyes, which can actually go to a face. The output of car can be its windows, right? Or tires. Elephants can be its trunks. Chairs can be its, whatever, its things can be, right? So these are the intrinsic features that one has to learn, right? To actually reach to face. There is nothing called as you can't directly reach to face. There was a question that is feature understanding learning? Of course, right? If you understand the features well, then only you can, join all of this together to detect and say that this is a face versus a car versus an elephant versus a chair, right? At its lowest level, all might like look same, but they will feed one after the other to have higher meaning on top of it, right? So that is what this idea of layering. We have to represent this hierarchy in layering, hierarchy in features that are to be learned. This is important. You can't directly just reach to face, right? What is the third one that is important from a image standpoint is this, spatial invariance, right? Whatever way you look at, it's very easy for us to um, imagine an image, right? You rotate an image or you revert it, you put a black and white, you blur it, does not matter. It is very easy for us to find out. Even in very low light condition, the same image in a black and white, you will be instantly able to recognize it. You have to learn. So the CNN or a network, or in this case a layer, has to learn this invariance. It has to learn that if my picture you put big or small, it does not matter. I will remain same, but the model might not, right? If my picture is in dim or very dark, if it is rotated in any form, right? So all these things, the layer or has to be invariant of all these things. Is there a shear? Is it stretch? Is it contrasted? Right? So how can we build a network or or something for that matter in such a way that it should represent all these things at a very fundamental level, right? And all of these are ultimately what? These are nothing but numbers, right? So we will be discussing that how this particular type of neural network, what it does in such a way that the hidden layers, the output of those hidden layers are numbers in such a way that they represent these three, four things, which are crucial for to understand, images, right? We will see that if you actually see, this is a challenge that we have seen, right? ImageNet is a awesome challenge that has happened, right? Over the years from 2010. This represents actually the error rate. Okay, 28.2% was actually the error rate. Human error rate was sometime in human error rate was documented at 5.1%. If you remember, ImageNet was this massive, 14 million or some 1 million images or something. I think it has now blossomed to 14 million, but at that time it was 1 million images with 1,000 classes, 1,000 classes. Okay, and and in 2008 or so, sorry, 10, 11, you can, and 12, right? 10, 11 actually, you can see this, right? So the error percentage was 28.2. In other words, this is my total error. So in other words, only the 78% of time or 72% of time the model was right. In a human case, you can see it's like 95% of time humans were right. And over the years, it has reduced. If you remember that we've discussed AlexNet, so this reduction from 11 to 12, which actually fueled the the deep learning war. Remember, told you about it. So this reduction was like stunning, like 9-10%, right? Almost 9%, right? So people were shocked, right? What has happened, and what has happened was that AlexNet has happened, and from that it was steadily gone down till 2014. Do you remember this thing, Sezeskis? What is this? 2014 GoogleNet, and then after 2014, before ResNet, what they did is that there in between 2014 and 15 there was one more model, and we've discussed that day. This was a model with batch normalization, which actually reduced from 6.7 to 4.9, okay, or something like that. So there was this model which only added this using GoogleNet and added batch normalization after every layer, okay, and that is when batch normalization was invented again on images, right? But then it continued to go down, right? And you can see these layers. It was 8, 8, 8, then 19, 22 layers, and then from 2005 152 layers, or 152 layers, right? That's a massive jump of layers, right? It's a really large network. So this we will see. These are very popular CNN structures, and you will see that nowadays, if you have to train an image detection or a classification system, you will not start from zero. Okay? Why? Because these models, sorry, these models, they have already published this world understanding, and you can use that as a base. So you don't have to start from 28.2. You will start from 2.3. Okay, and from there you can actually improve means what, you can just as it is use it, and your base understanding of any image is almost done. If you are going to suppose you will use a very specific sort of image structure like X-ray and all, which these kind of images have not seen, but however people say that use the basic structure that this kind of CNN gives you, so that the the idea of vision is been already been provided to the model, and on top of that you add your and do whatever you want to do, test, train and all. That we will actually also discuss very briefly on transfer learning and how it is changing the whole game. Okay. um, right, so these are the very famous model. LeanIt is nothing but Jan LeCun's, I think. This is what he's made, and it was deployed in a bank, or I think post office or postal system, because it needed a lot of data, right? There was no data available. AlexNet, right? It revolutionized. VGGNet is a very, very popular, it's still used. In fact, the backbone of many of those things is VGGNet only. ResNet is from, I think it was from Microsoft, which, used this residual network, okay? One of the reasons, right? They have moved from 822 to 152. I think in the paper it was mentioned that they were facing exploding gradient. So they started taking those older weights and computing it again. This is called as the residual network or skip network, something like that. Okay. If you see VGGNet, it's like this thing, some layer, and then pool, some layer, and then pool. We will discuss this. What are these layers? Okay. What is the convolution layer? I'll talk about. We will discuss this. And it basically says about there are VGG16, VGG19. There are two types of layers that we have, but it has, you can imagine, right? VGG16, like 6-7 years back itself, was 132 million parameters. Pretty deep model itself, but it's not that big actually. Though the layers are not there, but it's okay. It's an average model nowadays, below average model. ResNet is much bigger model. It has 152 parameter layers, and there is ResNet 50 also is there, which is 50 layer model. There's variations of it. Okay, and these are fairly very popular, very popular networks on image. And you will actually discuss this transfer learning and fine tuning. It's a very common way to do it. If you are someone who's using image, you will 99% of cases will start from a VGGNet or a ResNet or something like that. Okay, and then you will add those last layer and do fine tuning. Okay, so that is what it is. You can in any of those layers you can say that I'll freeze my first n number of layers, only my last layer will be trained. There are techniques that we will see. The major advantage of this kind of CNN structure is again feature engineering. Image is a hard thing, building feature is extremely difficult, and again the same idea of neural network continues, where this large network can actually build those three things that we spoke about, right? Local connections, layering, and spatial invariance in each of these numbers that we generate. And that's why these things can actually be so great. Okay, we'll stop here. Okay, and we will continue tomorrow. But so that is where we'll see that how, what is the core of CNN, how do we actually do it. It's actually a very simple operation as with anything else, and goes back to signal processing, the way people use, because image was a big problem at that time, and you will see that how it is resolved. Okay, we will stop here. If you have any questions, let's get something clarified. But I would say that now that you are deep learning, armed with the understanding of deep learning, we are now going to specialized networks which focuses on solving specialized problems. Okay, tomorrow we will go through CNN, and day after, on day after tomorrow, we will do recurrent neural network, which is a time series kind of a thing. It is also used heavily in NLP, but we will not touch NLP. That is outside the scope. We can discuss it and its usage. It's also a type of a network like CNN, but completely different, focused on something else. Okay, and we'll see that this idea of NN, neural networks, is now used, and then highly optimized types of network are getting built. But the fundamentals will continue to remain same. Everything will be forward passed, everything will be backward passed, everything is weights and biases, and we need to find that new weight given an old weight and some sort of gradient of a cost function. Okay, so that is a game that we are in, and we will try to go through again and again. Okay, do you guys have any questions? Is it too much? Is it okay? Do you want more samples? I'm all ears. Okay, let's try to make use of our time, and I can give you more help or material if you need so. Okay, what you can do maybe is that go start the project. Okay, that will be a great place to start and tinkering around the code. We can discuss, maybe what we can do is like on a daily basis we can focus 10-15 minutes of time focusing on the projects. Maybe it will be helpful for everyone as well, right? We can do that. That is not a problem. Okay. Do you guys have any question? Let me know if you have any questions. What we'll see tomorrow is this, what we'll discuss tomorrow is that we will discuss again this part, but in our explainers, so that we understand what are we trying to deal with, why suddenly there is a C now. Okay, what is this convolution operation, how will it help us, how does it help us, and its inner workings of a CNN. And then with assisted practice we can complete CNN tomorrow. It is not a big lesson, but the primary reason it's not been targeted as a big lesson because advanced computer vision is a separate course, and working with image is a heavy duty task, and we will see that why it is so. Okay, and its popularity as well. We are 5 minutes to the closure. If you guys have any question, Can you share any PDF or book? On deep learning, I've shared a book. You can use Jan Goodfellow's book. It's pretty good. Okay. Jan Goodfellow's book. Just go to Google and search for Jan Goodfellow. Okay. Jan Goodfellow was the father of, he is also considered as a, he was the one who in his PhD thesis spoke about GAN, right? So it's an open book, and you will see some sort of commonality in what we are trying to do. Okay. And the language also is very nice. It's also a very good book from so I can just give you the link, right? Let me just go there. Jan, I think I've given Jan Goodfellow. Yeah, so this is what it is. Deep learning book. There's only one book, not one book. Sorry, this is good book. So you can see this, right? This is Jan. This is a good book. Okay, it talks about a lot of practical things, right? D2L, there's a lot of, yeah. D2L.ai is also good. But this is a very popular book. You can also get you cannot get a PDF out of it. It's also only a website from MIT Press. There is also a book from Francois. One second. Francois, the founder of this thing, Keras. This is the guy who actually written. This is the creator of Keras, by the way. Okay, he created Keras. Okay, so Francois Chollet. He has a this book, Deep Learning with Python. Okay. Yeah, you can do that as well. Yeah. So this is I was talking about Deep Learning with Python. This book. Okay. You can see this, but this is a book. Okay. It's like a hard copy book. Okay. It's good that if you can actually get this also. I like this book. I liked the book. Okay. There is yeah, I think there's many books are there, but I think I like this. This two book is definitely on top of my list. Hands-on machine learning with Keras and Python. Yeah, not bad. Yeah, let me see. I think it should be good as well. Any book by O'Reilly is generally good, na? Who has written it? Yeah. So there's a lot of hands-on, right? So this is it's good actually. This is sklearn, Keras, and TensorFlow. So the other two books gives you intuition and then it's just not code, but I think intuition is important in many places. Okay, yeah, Python Deep Learning Cookbook. Yeah. Okay. If you wanted to, there was a discussion that you wanted to. Do you follow this guy? 3 blue 1 brown. What is his name, man? 3 blue 1 brown. Yeah. Yeah. So follow that guy. Okay. Yeah. He's a Grant Sanderson. He's a young guy, but the way he explains his videos are awesome. In fact, if you wanted to know about backward propagation, is an awesome video, man. This backprop. Yeah, see this video. This is like really good representation, and the way he explains is like it's really good. Okay, especially, and then of course, if you want, you can actually go back and do the calculus part of this, and then come back to it as well. So he explains it, and then with that animation, really good. Okay, lot of hits, huh? There's a lot of songs like at least like now 5 years back, 4.5 years back that is done. So that is also a good place to do. I also like this guy Josh Stratum. Who's that? What is that? Josh. What is his name? Josh Bam. He keeps on saying Josh Bam. What is this guy? I forgot. I'll tell you guys later. Okay. So he also makes nice tutorial and basically explains things in a very easy manner, right? And what you can do is like whenever you want to watch Netflix, instead of Netflix, watch one of this 10 minutes video. right? It's just like whenever you are free, you can just watch one of these videos. It just sets things in your mind more and more and more. That's all it is, right? Amazing. No, Josh Gordon. What is this? Josh Strummer. Josh Strummer, actually. Josh Strummer. Let me. I can. I'll send you his. I'm there with his in his LinkedIn. But I like his this thing. Okay. Fair enough. Then let's call it a day today, and let's come back tomorrow. We'll do CNN tomorrow. We will actually see. We'll do two this thing, two notebook files, and then we'll see. Then we'll give our understanding of image processing and convolutional neural network. Okay. Awesome. Anything else, guys? Let's catch up tomorrow, guys. Then. Okay. Thank you. Have a great night. If you are in this part of the world, thank you very much. Thanks a lot. Thank you. Indeed. Good night. Good night.